A2 Maths using reciprocal functions. Right, so what I'd like you to do is just these 8 quick questions on the board using your Year 1 skills. Just see whether you can find all the solutions to these trig equations. So just pause, take your time, have a go at those solutions. We'll look through the answers in a minute. Right, see what you would have done. So you can do it without graphs, but it's always worth making sure that you're aware of what the graphs look like. So for the first one, for example, is our sine graph, and we're looking for when the function equals 0.5. So we've done it between 0 and 360, so we can see we're going to get 2 possible solutions. That's the benefit of having a quick sketch. We know exactly how many solutions we're looking for. We can find the first one with our calculator, and the secondary solution using the fact that there is some reflection going on. So we know it's that far away from there, so it's going to be the same distance from 180. So the first answer we got is 30 degrees. 30 off 180 is 150. There will be my 2 answers. Let's look at the second one. Cos 4x is minus 0.7. So the first thing you should do in these graphs is think, right, because I'm dealing with 4x, I need to change that to 4x. So instead of going from minus 90 to 90, I want to go to 4 lots of 90. So I'm going to be looking at the range minus 360 to 360. We're looking at 4 times the range. So what do I get? There's my line of minus 0.7. I'm ignoring the graph of cos 4x. I'm just drawing the normal cos graph, but the 4x is coming in the fact that I'm increasing my domain. So what do I get? Well, the calculator can get me the first answer. Fantastic. I can use symmetry to get the second answer, it's either side of 180. And then once I know that, I can then add or take it away to any amount of 360. So that would get me that one. And taking away 360 from there would get me that one. So I can go through, hopefully get those 2 answers. The other thing about cos graph, the other option you have, is once you've got your primary and secondary solutions, it's symmetrical about the line y equals x. So because it's reflected there, you could just use those 2 as the negative versions. Okay, that's what 4x equals. But that's what 4x equals. I want what x equals. So what do I do next? To pull it within this range, I divide each of those answers by 4. And there we go. There's the answers in that range. Tan x minus 20 equals minus 0.15. So the first thing I'm going to do is deal with the range, the domain. I'm going to be looking at changing the domain. Instead of x minus 20. So I'm going to go to 20 and 380 because I'm going to add 20 to each of those. So what do I get? I'm only interested, look where I've done it from, minus 20 just here up to minus 360 just here. So to change that to x minus 20, I must have taken off 20 from each of these sides. Right, how many solutions am I going to get then? I'm going to get one there that I could have so easily missed. I'm going to get one here, and I can ignore this one over here because it's not going to be within my range. So my answers are going to be minus 8.5 and 171.5. It's very easy to ignore that one because you might think it's not within the range. Okay, now once you've got both those answers, how do you get the correct answers? I need to add 20 to each of those. There we go. 11.5 and 191.5. When you take away 20 and do tan, you should have got that function just there. What's next then? 3 cos blah blah blah. So when you're coming to rearrange this, the first thing you want to think about is getting rid of that 3. So divide it by 3 first of all. Because if you didn't, you wouldn't be able to do cos to minus 1 of 1.8 anyway. And the second part is dealing with this radians just here. So instead of x, I want to write it as 2x minus pi over 2. So what can I do? I can take away pi over 2 from both sides, and I can double both of them as well. So really, I'm looking at working between minus 0 is just going to be from minus pi over 2, so it's just there, and this side would be 4 pi, so it's 2 pi, 4 pi minus pi over 12, so just there. Now, if you didn't quite get that, if you go from 0 to 4 pi because you're dealing with 2x, it would probably be fine. Okay, if you just drew the graph from there to there, in this case, it would probably be fine. Okay, so you don't have to worry about being very precise on your graph. As long as you can see you've got 1, 2, 3, 4 solutions. What you do then, get your calculator, get the first answer. From that first answer, using symmetry, you can see that it's the same off 2 pi, or just take it off 100, add it onto 180 if that's what you want to do. But you have to work out that distance just there. So what do we get? 5.356. Once you know that, you can do that plus 2 pi gets me that one, and that plus 2 pi gets me that one. Now these values are what 2x minus pi over 12 equal. So therefore I still need to add pi over 12 to each of them and then divide by 2 to get me the values within the range from 0 to 2 pi. Okay. Tan squared theta equals 4. So the first thing I want to do is get rid of that squared. Don't make a silly mistake and say that means that tan theta equals 2. That's not true, or it's only half true. The other answer you could have is tan theta equals minus 2. So when I come to sketching my graph of tan theta, I'm going to look at two equations. One where it equals 2, one where it equals minus 2. Now in that case, I'm going to have 1, 2, 3, 4 possible solutions. So I can use my calculator. Calculator will get me the first solution, okay, which would have been 1.11, and minus 1.11 for minus 2. I can then use that fact to do add 180, or take away 180 in this case. Gets me that. Of course, because it's not 180, it would be just pi. Or I can add pi to that one to get me to there. So that plus pi gets me 2.03. So there would be my 4 solutions. And in this case, you're not dealing much with the theta, so you can just write those answers straight down. Right, so when you get to number 6, this is where it gets a bit more technical. Because for number 6, you've got to do some rearranging. So in number 6, I'm thinking 3 cos theta sine theta plus cos theta equals 0. The first thing I'm going to do is just factorise cos theta. Now you might be thinking, oh, I'm going to use all my trig identities, you know, the tan theta equals sine over cos, or the sine squared plus cos squared equals 1. But just be aware, you can just factorise this. And if you factorise it, what you're going to end up with is cos theta brought out, and inside the brackets, 3 sine theta plus 1. Cos theta times by 3 sine theta plus 1. That leads to 2 possible sets of solutions. Either the cos x graph, which is just there, must equal 0. Okay, that makes sense, because if cos x is 0 and cos x is 0, you're going to get 0 plus 0 equals 0. So I could have that graph, or the other graph you could have is the 3 sine theta plus 1 equals 0 when I factor out a cos theta. 3 sine theta plus 1. Now that's that graph. Okay, drawn just there. Notice it's only between 0 and 2 pi. I will deal with the 3 sine theta plus 1 in a minute. What do I need to do? I'll rearrange it so that I get minus 1, and divided by 3 is minus a third. There's my line of minus a third. So just to make sure you're happy with that. So this could get me cos, open the brackets, 3 sine plus 1 equals 0. So either cos must equal 0 or 3 sine plus 1 equals 0. Now if the 3 sine plus 1 equals 0, 3 sine plus 1 equals 0. That yellow pen's rubbish, so we change it to a different colour. Change to green. So then I can rearrange. So that means that sine theta is going to be equal to minus 1 when I rearrange this. So minus 1 over 3. Okay, and that is where this line here comes from. Okay, so I need to find the solutions to that as well. So I'm going to have two answers, that one and that one. When I put it in my calculator, it produces this answer down here. So I'm going to have to do some thinking on this one. I'm going to get the negative answer, but I can get this positive answer. I can also work out how to get it from there as well to get me 3.46 and 5.96. These two answers when cos theta equals 0, gives me those two answers, and so then I can put those in. Okay, get rid of those. There you go. Right. Sine x equals 3 cos x. So when we think about rearranging this, I would be thinking, actually, I can't do like I just did here. I can't factorise, but I can do some rearranging because I've got sine, and I can divide it by cos, and it's going to equal 3. So a simple bit of rearranging. Cos x can go underneath, and I'm going to get sine over cos. Now, what I know about sine over cos, though, if I look at that sine over cos just there, I know that that is exactly the same as tan. So what I can do is I can replace it for tan theta equals 3. And so what I end up with is I end up with just something I could work with on the tan graph. So there we go. There's my tan graph, because it's tan theta equals 3. So I'm going to get a solution just there, 1.25. And if I look across, I don't have any other solutions. So this answer just here is going to be just 1.25. Okay, right, let's look at the last one. There's no surprises, you just used one of the trig identities. So on this one, I'm going to have a look at using the other trig identity. So in this case, I can't factorise like I could do in number 6. Can't factorise like I did there. I can't use the fact that sine over cos is tan because there's no easy division, but I can use the fact that I can change sine squared to cos. Now I want to do that because then hopefully I will have some sort of quadratic equation. So let's have a think about this. I'm going to have 5 equals 6 sine squared x plus cos. Right, so I'm going to have that. Now I know that the sine squared just here, I can use 1 equals sine squared plus cos squared. That's atrocious writing. I do apologise. But 1 equals sine squared plus cos squared. That means if I rearrange this though, I can change sine squared to 1 minus cos squared. So 5 equals 6 lots of 1 minus cos squared x plus cos. Right, so that is a lot more helpful because I can rearrange it and hopefully write it as a quadratic. So I'm going to go to the top of the page just because I've got more space. So I'm going to write it as 5 lots of, so 5 equals 6, I'm going to expand the bracket, minus 6 cos squared plus cos. Right, so a bit of rearranging. I'm going to take that to that side. I'm going to take that to that side to get -1. I'm going to take that to that side to get -1. Right. So if I do that, I'm going to get 6 cos squared I'm going to get 5 lots of, put an equal sign in, sorry, let me try that again. I'm also going to get minus cos, and I'm going to get 6 taken away from there, so minus 1 equals 0. Okay, so I've got that answer just there. Now if I do that, then what I'm going to end up with is something I can now factorize. So I'm thinking of two numbers that times together to make -1, but I've got to make 6. The only way to make 6 will probably be 3 and 2. So I've got 3 cos on the front. I've got 2 cos inside, and I've got equals 0 at the end. Okay, so I'm running out of space on this little board. So 3 cos, but I also know -1, so that's going to be like +1 and -1. It's the only way to do it, isn't it? So I've got to make minus cos. So I'm thinking 3 cos times -1 is going to get me 3 cos minus 3 cos. This one can be by plus, and that should work out lovely, shouldn't it? There we go. 6 cos squared plus 2 cos minus 3 cos minus 1 equals 0. So I'm going to have two sets of solutions. Either cos equals -1/3, which now I can solve because it's cos theta equals -1/3, or cos theta equals 1/2. So if you're not sure on that, you will get more practice with solving trig equations, but that was the bit that you should have done a lot more practice of last year. But now I'm in this situation, I can now try to solve it. So let's have a think. There's my cos graph. I'm looking at the two sets of solutions. All right, so let me just get my pointer back. There we go. So I'm looking at two sets of solutions. One when it equals 1/2, which I got from there, and one when it equals -1/3, which I got from there. Now I can get my solutions by solving it. So when does the cos graph equals -1/2 at 60 degrees and also at 300? And when does it equal -1/3? 109.5 and 250.5. So there are my 4 solutions. So very well done if you managed to calculate all of those. That was by far the hardest one because it involved you having to do the trig equation. Okay, right, but that was a big recap of your year 1 skills. So what we want to look at now is we want to look at moving on to some year 2 stuff. So grab your notebooks and let's have a go at working out this. Solve the equation cosec theta cot theta plus 2 cot theta equals 0. And I'm looking for the solutions of that over the interval minus pi to pi. So just give you a chance to write down your notebook, pause for a second if you need to, and let's look at the solution. So first thing I need to remember is what cot is, what cosec is, and what sec is. So those are my 3 equations. Now we did that earlier on in the previous lesson when we looked at the graphs. Now what you don't want to do is just dive headlong and suddenly start rewriting these as 1/overs. Okay, sometimes that might be necessary, but not always. Now if you remember the third from last one we just did, where we factorized, that's what you could do with this. So I'm thinking, actually I've got a cot theta there, I've got a cot theta there. So what I'd like to do is just factorize those out. Okay, so I can pull out the cot theta from both parts. And that's going to leave me, because it's equal to 0, to 2 possible solutions. Either that cot theta equals 0, or that cosec theta plus 2 equals 0. And if cosec theta plus 2 equals 0, that means that cosec theta must equal -2. Once I've got those 2 solutions set out, you might think, oh, now I'm going to draw the graph of cot. I'm going to draw the graph of cosec. Don't. You need to learn those graphs, yes, but you don't need to use them to solve things. So my advice now is to say, well, if cot theta equals 0, I know that when I look at my cot graph, okay, if I look at my cot graph, when does that equal 0? Just there. The other option, rather than learning the cot graph off by heart, is to say, what about the 1 over tan graph? Now the 1 over tan graph, or the tan graph, sorry, is something you would know how to do. And if you know how to plot the tan graph, then you would know that when is the tan graph equal to its asymptote is at minus pi over 2 and pi over 2. Okay, so those are your two choices. Either you look for when cot theta equals 0, in which case you need to think of the cot graph, or the other option is when does tan theta equal its asymptote. Now, because you know the tan graph off by heart, you probably know that the tan graph has its asymptotes at those two places. Okay, right, this one might be a bit easier to explain. So cosec equals minus 2. Don't draw the cosec graph. Think what cosec means. Third letter, S, means it's 1 over sine. Okay, so I can write it as 1 over sine. When does that equal minus 2? Now, rather than trying to draw the cosec graph, I know the sine graph off by heart. I know it starts at 0 and goes up and does all that. So I can now rearrange, just move the 1 over there, get the sine graph, and now I can sketch it and find the solutions. When sine graph equals minus a half, here it is, these two solutions. Like we just practiced at the start of the lesson, you can write down these two values. Once you write down those two values, add them to these two values, and there you go. You have all the solutions for that equation. Right, so what are the two trig identities you know involving sine, cos, and tan? So the two trig identities. Okay, so again, pause if you're not 100% sure, we give a bit of thinking time, but it shouldn't need long because we actually just use them at the start of the lesson. So for sine theta, cos theta, and tan theta, the only two trig identities you know from year 1 are either sine squared plus cos squared equals 1 and tan theta equals sine theta over cos theta. Those are the two you did in year 1. Now, unfortunately for you guys, you're going to have a lot more in year 2, right? A lot more of these. But also having lots more means you can do a lot more different questions. So let's have a think. First of all, what else can we do with these to get some new trig identities involving the reciprocal functions, sec, cosec, and cot? So the way we do it is to start with, we can look at what cot is. Now, cot is 1 over tan. Right, so you know it, it's the third letter rule, T, so cot is 1 over tan. But you know that tan theta is exactly the same as sine theta over cos theta. So I can replace tan theta from my year 1 trig identity skills, because I know it's the same as that. But I also know from GCSE that 1 divided by a fraction means that denominator can come to the top. Okay, if you're not convinced with that, all I'm doing is multiplying top and bottom by the same thing, which is cos theta. And so therefore, I get to that answer. If I multiply the numerator and denominator by cos theta, I get that answer just there. Now that is your new trig identity, okay, which you didn't have last year, which you can now use. If you see a cot theta, there's absolutely nothing wrong with you replacing it for cos theta and sine theta. Okay, so we'll keep that in a new bag of trig identities, and let's investigate some of the others. So I'm going to go back to this one then. I'm going to start there. Sine squared plus cos squared equals 1. And what I'm going to do is I'm just going to divide through. I'm going to divide through by cos squared theta. So I can do that. I'm allowed to divide every bit, so that bit, and that bit, by cos squared theta. So there we go. That's what I've done. I haven't done anything different. Because I've done it to everything, it's perfectly reasonable. But now that I've divided everything by cos squared, I can use some of our other facts. Look at this bit here. Sine squared over cos squared. Now that's the same as sine theta over cos theta squared. And I know that sine theta over cos theta is just tan theta. So really, sine squared over cos squared is just tan squared. Look at this one. Cos squared theta over cos squared theta. Numerator and denominator are exactly the same. This is definitely going to be equal to 1. And finally, look at this. 1 over cos squared. Now, 1 is like 1 squared. So really, this is 1 over cos theta, all squared. I could quite easily write it like that if I wanted to. Brackets, squared, get rid of that bit just there. It's the same as 1 over cos theta squared. They're identical. What does that mean then? Well, I know that 1 over cos theta is exactly the same as sec. Third letter, C, it's exactly the same as sec. Okay, so I can replace it. That's my tan squared. That's my 1. And 1 over cos is sec squared. Tan squared plus 1 equals sec squared is a new trig identity that I could use from this. And to get the last one for now, what I'm going to do is the same trick again. I'm going to start with sine squared plus cos squared equals 1. And I'm going to divide through by sine squared. So there we go, divide through by sine squared. So I get sine squared over sine squared, cos squared over sine squared, 1 over sine squared. Right, and let's go through. Well, sine squared over sine squared is just going to be 1. Cos squared over sine squared is the same as cos over sine, all squared. But cos over sine, that's one of the ones I just got. That's cot theta. So really, that's cot theta squared, or cot squared theta. And finally, 1 over sine theta, all squared. Well, 1 over sine, third letter, cosec. So really, 1 plus cot squared equals cosec. That is my final one to learn for now. Those are my 3 new trig identities. You've got to learn those off by heart. My advice to you is just to arrange them. I'll show you what I would always quickly do, because it's very easy to make some silly mistakes on those. So for this one, you just saw me do it, but it's really quick. Sine squared plus cos squared equals 1. So if I don't remember which one, I'll go right. I'm going to just quickly divide through by sine squared. So there we go. Divide through by sine squared. Divide through by sine squared. Ah, look, I've got 1 plus cos over sine is cot. There, 1 over sine is cosec. 1 plus cot squared equals cosec squared. There we go. That's how I got that one. Okay, very quick and easy to learn this sort of idea. But if you're good at remembering formulas, great. If you're not so good, learn how to get them really quickly. Okay, right. So let me just quickly rub this out. So once you've got that, you need to learn those identities. So I'll give you a chance to get them in your notebook. If you haven't got them already, get them down, learn them, or learn how to formulate it like I just showed. Right, give you a chance to write the question in your notebooks. Pause if you need to. And let's look at using some of those new trig identities to help us solve this trig equation. So 10 sec x minus 5 equals 5 tan squared x on the interval 0 to 360. So how am I going to do it? Well, the first thing I'm going to do is notice that I've got a tan squared. Because I've got a tan squared, I'm going to pick out one of my trig identities that's got tan squared in. Okay, so the one that had tan squared in, if I've forgotten what has tan squared, well, if I know that sine squared plus cos squared equals 1, and because I want tan squared, I know that tan is sine over cos, so I would do that. Cos squared. So what's my trig identity? Oh, I know what it is. It's going to be sine over cos, tan squared, plus 1 equals sec squared. And that's where that bit comes from. Okay, so if you're not good at remembering formulas, don't blame you. Learn how to get them quickly. Okay, so I've decided that I'm going to try this. The thing about trig identities is sometimes You might pick the wrong one. It might end up in a bit of a pickle. So you go back and try something else. But let's just start with this one and see if it works. So the tan squared. If I use tan squared, I can do a bit of rearranging. Look, I can bring that over, make tan squared the subject, and I can rewrite it as sec squared minus 1 equals tan squared. So I'm going to substitute that in for just there. So really, 10 sec minus 5 equals 5 tan squared. So therefore I can substitute that part in. I can expand it to get that. I can now rearrange, and if you haven't noticed it already, you've got another hidden quadratic. You've got a sec squared, you've got a sec, and you've got these two numbers that you can put together. So if I put them together, what's quite nice is the 5's cancel out. I end up with that quadratic equation. A nice easy one to solve because I can just factorise. Don't do something silly like dividing through by sec x. You must try to factorise. So there we go. What have I done there? Just checking. If you didn't do this, it's not the end of the world. I just divided everything by 5. I'm allowed to do that because 5 is just a constant. But if you didn't do it, it's not the end of the world. And then I can factorise. So I know now that I've got sec x, lots of sec x minus 2. And now I can solve it. So what does that mean? It means either sec x equals 0, okay, or that sec x minus 2 equals 0. In other words, sec x must equal 2. Interestingly, that first one, that sec x equals 0, has no solutions because, as I said before, sec x can't equal 0. The range of sec x is 1 and up or minus 1 and down. It does not have any solutions in the middle. So that one I can ignore. Okay. Sec x equaling 2 does have some solutions because I can rewrite that as 1 over cos equals 2, and then I can rewrite that to get cos equals a half. Notice I've just done the reciprocal of it. So the reciprocal of that and the reciprocal of that means that sec can go to cos. Okay, so if you want to convert sec to cos, you just take the reciprocal of the other side. Cos equals a half. Get some solutions. There we go. There's the first one my calculator tells me. 60 degrees. Take that away from 360, 300. There's my two solutions. Right, so once you've got your two solutions, that equation, you can move on. So just pause, give you a chance to pause it yourselves in case you haven't got it all down. And then when you're happy, move on. So what I'd like you to do then, please, is on exercise 4.3 on page 262, just have a quick go at those questions and make sure you're capable of solving some of those new trig identities. Okay, and then move on when you're ready. Okay, so what we're going to look at is a slightly new question. You've done a few of these in year 1, but not many because you couldn't really solve that many identities because you only knew 2 trig identities to use. So get down your notebook. Let's see how we go about proving an identity. Right. Notice it's not a solve question. So a solve question, like you've just been looking at, are ones that involve you having a range or a domain, I should say, to actually work with. Whereas this one's not. The goal of proving identity is to start on one side of the equation and work out how to get the other side. Now the key thing is that you don't need to use just one side. You can use a mixture of two sides. So I could, if I want to, I could do a bit of work on there and I could do a bit of work on that side and see if I can get to something that's the same. That's what you're trying to do. But what's important with a proved identity is you're not allowed to do operations that involve both sides. So I'll show you what I mean. Okay, so when you're asking to prove the identity, you're trying to rearrange either side, like I just said, to get to the other one. You're not allowed to perform operations that act on both sides. So you can't do something like adding 2 to both sides. You're not allowed to do that. You're not allowed to double both sides. Okay, you're only allowed to operate on one side and work on one side to get to the other. So you're not allowed to multiply both sides by 2. Make more sense when we actually have a go at doing it. And yeah, in this case, you wouldn't be allowed to take away. It seems really logical, doesn't it? Can I just take away cot theta from both sides? Take that over there, make it minus cot theta. It seems perfectly logical, but that doesn't help you prove an identity. You're not allowed to do it to prove an identity. You're trying to prove that this side gets to this side. Okay? So the best way to stop you making that sort of silly mistake is to almost separate it into two columns. If you separate this into almost like two separate questions, it will stop you trying to rewrite them. So I would write them as, rather than writing in equals, I'd write them as two separate expressions. So there we go. Expression on that side, expression on that side, and I'm not going to do something that works on both. I can play with this, I can do some work on this, I can do some work on this, but what I don't do is do something that happens on both. So I can ignore it. Right, so what can I do then? Well, you can do anything you like using your trig identities. So my trig identities, I know, for example, that tan theta is exactly the same as sine theta over cos theta. I know that cot theta is the same as cos over sine. It's one of the ones I just learnt. So I can use those two facts here. And that's what I'm going to try first. This is one of those things that sometimes you try something, it doesn't really help, so I'll go back and try something else. But let's just try that first. So tan is the same as sine over cos. Cot is the same as cos over sine. If I've got two fractions, I can put them together as long as I've got the same denominators. So I'm going to do the same denominators, and I can carry on working with this. Or, if I want to, I can just have a play with this one. This one here is 1 over cos, 1 over sine. They go together to get 1 over cos theta sine theta. I might look at that and think, well, I'm a bit stuck now, so let's go back to this side. Or I could just concentrate on one side. It's totally up to you. Okay, how you do these. What your goal is though is to get to the same answer on the bottom of both of them. So here I'm going to try putting these two fractions together. Now I can do that as long as I have the same common denominator. So here, if I multiply by sine theta, that would work. And this one, if I multiply by cos theta over cos theta, that would work because I'm not doing anything wrong there. I can now put them together because I've got a common denominator. Sine theta to me is sine squared. Cos theta to me is cos squared theta, cos squared. So really I get that. But I also know that cos squared theta and sine squared theta added together is equal to 1. So really, there we go. I'm sorted. I've got down to this answer. I've noticed it's the same as that. So therefore that is the same as that. So I've got this progression going down here. This is what I'm looking for. I'll try the yellow pen out. I'm looking for a progression that goes from there and then goes round to there. That's what you're looking for. Okay? And as long as it works either way round, that's great. Okay? So I can stop. I've proved the identity now. What some students like to do is they like to, at this stage, just write that last answer. So therefore that goes to sec theta, lots of cosec theta. And so therefore there's a nice clear pattern taking you from the original down to the end. So you proved it from that way. Okay, that's totally up to you. Okay, as long as you're nice and clear for the examiner that you've actually worked it out. Right, just get my points back on. Okay, right. Yep, just said that. So proving both the same. So put that in. There you go. That's a lot neater than my hideous mouse scrawling a minute ago. But you've shown the route to get from one to the other. Okay, right. So stick this in your notebook, but feel free to have a go yourselves. So you want to pause, have a play yourselves. You might get into a pickle. Don't worry. You might not want to stick it in your notebook straight away. Right. And let's see how you get on. Right. So I'm going to draw my line. So I don't do something stupid like times it by 1.1 minus sine theta. All right. That's quite common. You might look at it and go, oh, I'm going to times by 1 minus. No, you can't do that. It's prove the identity. So what can I do then? This side looks a bit difficult to do anything with. This side though, I can expand. Okay, so that's what I'm going to start with. Sometimes it's a bit more obvious which bits to play with. Okay, so I've got to that. Carry on playing with this then. So I've got tan squared. Sec squared, I'm going to expand to 1 plus tan squared. Okay, so I'm decided not to make life too complicated and change two things. I'm just doing one thing at a time. So I know that sec squared is the same as 1 plus tan squared. If you decide to change tan squared to sec squared, that's perfectly okay. All right, it might help, it might not. This might help, it might not. I've just got to try things. What can I do then? Well, this is a bit of a jump. You might think, oh, I never would have got that. That's quite common. Don't worry. When you've practiced enough of these, you might start to spot how to do certain things. So what have I done? Well, I've divided or rewrote everything in terms of sine over cos. So we've got tan squared is going to be sine squared over cos squared. Notice there's two of those because I put those two together. So there's two tan squareds, two tan squareds. This one here, I've changed the tan to sine over cos. I've changed the sec to 1 over cos. So that's where this has come from. Two lots of tan times by sec. So 2 tan squared sec. And 1 is just left there at the end. So all I've done is just tried to rewrite it now in terms of sine and cos. And I might think I'll do that because I'm trying to get to an answer that's got just sines in. So I don't want tans. I don't want coses either. So we'll see if they disappear. What can I do then? So that step, what I just did there, is that's the same. That bit there was the sine over cos and the 1 over cos, got to be cos squared. And number 1, I've changed it to cos squared over cos squared. And the reason for that is because I've noticed I've got this common denominator, cos squared, cos squared, cos squared. And because I've got a common denominator now, I can put this together. So I've got this. Right, why does that help me? Well, certainly the top is getting a lot more sines. I'm still stuck with a cos squared and a cos squared, but I can deal with those. And I can change those to the sine theta because I know that cos squared plus sine squared equals 1. So really what I'm going to do is just change those cos squareds to 1 over sine squared, 1 over sine squared. Right, let's try to neaten this up a little bit because it's a bit messy, isn't it? So I've got sine squared theta plus 2 sine theta plus 1. Okay, that to me looks like a quadratic. So maybe I can do something with this. I can rewrite this or factorize it. Also, the bottom, you always need to remember, this is very, very common, okay? The difference of two squareds. So this idea, the difference of two squareds, I'm going to write it down for you, okay? If you've got an a squared minus b squared, then you can write it, so that bit just there, you can write it as a plus b and a minus b. And that's what we mean by the difference of two squareds. If you've got a square number take away another square, you can rewrite like this. Now you might not look and think that, but there's 1 squared and there's sine squared. So I could definitely write this as a difference of two squareds. So I could factorize that as well. And in fact, that's what I'm going to try to do. I can factorize the top and I can factorize the bottom. And if I do it, I'm going to end up with this answer just here. Notice the bottom was using that difference of two squareds idea, so I can still see it works. Look, 1 times 1 is 1. 1 times minus sign is minus sign, but 1 times plus sign is plus sign. So they two cancel out. And I've also got sine theta times sine theta is minus sine squared. So it's definitely right. And the top is just that bit. Now, why has that helped me? Because I can see now that this and this can cancel out, leaving me the answer I need. A lot tougher than the previous one, but don't worry, it will come with practice. The more you practice these things, the easier they become. The more you see. So that's exactly what I'd like you to do now. Have a go at exercises 5.1 and 5.2 and really just take your time. Take your time with it. Practice all those equations, practice all those proven identities. You'll start to see a lot of patterns coming up, but only if you keep practicing them. Okay, it's no good just doing one or two. Right, so I'll leave you with that. I'll take next to our lesson in a minute.